Today we're going to take a look at solving equations and inequalities by graphing. A couple of different ways we can solve by graphing. We'll take a look at these. We're going to use mainly today graphs. We do have in our clear learning target tables, but we're going to mainly stick to graphs. But we can solve them using tables, graphing technology. Of course, that's a graphing calculator to find the approximate solution for the equation or inequality. And we are going to find the approximate solutions to equations and inequalities by setting up the expression equal to y and then graphing. I actually prefer to do it this way. We'll see when we get to those how we will take a look. So we're going to just do this model and discussion. It says a homeowner has 32 feet of fencing in which to build 3 sides of a rectangular chicken run. Ask us to make a table with the lengths and the widths of this rectangular shape, and then write a function for the area. And I'll also show you something I've done through, this is Desmos over here on the right, but we can use this. So what we have here is if I have a side of 1, the other side I have 15, because remember we're building 2 sides on this. And we actually have 3 sides. I just stuck to a 4-sided one just because I wanted to get the idea of this. But we do have 4 sides. But remember, the perimeter of a rectangle is equal 2 times the length plus 2 times the width. We could have changed this equation because if we have one side that we're using the barn, it would just be length plus 2 times the width. And that's how much perimeter we would have. But just for the argument in the model we have here. So if I had a side of 2, it'd be 2 sides of 2, that would leave me with each of the other sides equal to 14. And if you're wondering, well, that only adds up to 16, but remember we have 4 sides here. So if we have these 4 sides, that would add up to 32. So if I had a side of 3, I'd have 13 for the remaining sides. 4 is 12, 5. You can see as we go through here, and then we finally get to 8 and 8. Now we continue the graph here, but you'll also notice that if you have a side of 7 and a side of 9, 9 and 7 is the same shape. We're dealing with the same shape, just on the other side. So as we take a look at this, I've created on Desmos an equation that will calculate these. So you notice I labeled my table x1 and my second one x2, and then I came over here and said x1 times x2. So remember, area is length times width. So this is a representation of my length, and this is the width. So 1 times 15, we would have an area of 15. 2 times 24, 14, excuse me, will be 28. And you can see as we continue to move up, our area increases. When we get to our 8, 8, we have an area of 64. But let's take a look. So a lot of people would make the assumption, well, the higher this number gets, the higher the area will become. But when we move to 9, 7, you can see that our area starts to drop again, because it is that same rectangular shape, like we said, that this one has. It's just the opposite length and width. So you see our area continues to drop. So we find on this, and by the way, the best shape, quadrilateral, 4-sided shape you can make to maximize your area is to build a square. We'll talk about this one. Would be a little bit different because we don't have to do one side, but we'll get more into that later. So as we take a look at the model that we have here, we see that we have this parabolic shape. So we have a parabola that comes out of this. And then we hit that maximum area when we had 64 or an 8 by 8. So we maximized our area at that point. So we have a good look at what this area does. Now, the last thing we talked about, we have here, is it says explain what would happen, what happens when the graph intersects the x-axis. Well, let's take a look at this graph again. We have this labeled here at the bottom. Now, on our application, when we're on that x-axis, what we have is no area because we have no sides. this would be a side of 0 and another side of 0. So we can't have this. This is physically impossible when we look at our x values. And then we look again, it says make sense of the, get this over here for us. Make sense of the width in the area. For what widths will the area of the chicken run be at least 55 square feet? Now, we see that this happens at 5'11" and of course 11'5". Now, it does say at least 55. So if we have a length or a width between 5 and 8, either one, if we have a length between 5 or 8, and then on the other side, 9 through 11, we're going to have an area that's greater than or equal to 55. So as we take a look at this, we see we have an absolute value equation on the left side and a quadratic equation on the right side. And then it says we want to solve this by graphing. So what we're going to do real quick is we are going to graph these one at a time. So my absolute value is going to look like we have here. I've highlighted the x values because if we only had the absolute value of x plus 2 minus 3 set equal to 0, these would be the solutions. It's very important that you get this message right now, early. It's going to benefit you majorly. Anytime you have an equation that is set equal to 0, anytime you have an equation that is set equal to 0, the solution will be any time that it crosses the x-axis, like we're seeing here. So that's why I highlighted those for you. It's not what we're looking for here because we're not trying to find the solution to this equation. We are trying to find when this equation is equal to that. But I felt it's important to take a look at that. So I'm going to next graph the second equation, which is the quadratic equation, x squared minus 6x plus 5. It looks like this. And again, you can see that I've highlighted the x values. That would have been the solution to that equation if that's what we were being asked. But what we have here is two equations set equal to each other. So when we have two equations that are set equal to each other, what we're interested in is when they intersect one another. Remember, these are the output values of the function. This red line is a list of input-output values. So when, for instance, -2 comes in, -3 is going to come out of this equation. That is our input, -2, output, -3. So when these two equations are equal, what we're looking for is when their y's are the same. So this is what they are when they're equal, but what we're looking for is when are they equal. As I told you throughout this year, Algebra 2 is a lot more focused on the x value than the y value. So the first thing it says, of course, is to circle our intersection points. Well, we see they're intersecting at the point 1, 0, and then again at 6, 5. So these two equations are equal at two places. So write an x value for this answer. Again, only the x. So these two equations are equal when x is equal to 1, and then again when x is equal to 6. So we'll take a look at these as well. We're solving when this equation is equal to 15. What I'd like to do on these, I'm going to show you probably the most popular and most common way to do these is I call it when I'm doing ACT prep to gather and graph. This is a really good way of seeing the answer. And basically this is being set equal to 0. When we have it set equal to 0, all we need to acknowledge is where it crosses the x-axis. So having said that, I subtract the 3 away from both sides, and what I end up with is the equation 5x minus 15. And again, set equal to 0. So I'm going to show you what this looks like. I go in here and on my graph, I graph it. And since it is set equal to 0, again, remember, that means when y is equal to 0, and when y is equal to 0, we cross the x-axis. So this equation crosses the x-axis at 3. Therefore, the equation we're given has a solution of x equal to 3. Now the example B is a little more involved. We got a couple of things going here, so we'll go through and we'll graph these piece by piece. So we have our graph, and I graph this, and what you'll notice is I have two solutions. On the next slide, I'm going to show you how we use the calculator to find these exact points when they're not so clear cut, like this one, 4.5. You can't really find that in a table. It's going to be hard to plug in. But again, we are interested in the x value. So when we graph these two equations, I could have set them equal to 0 and seen where it crossed the x-axis, or we can do it this way. So I see that these cross at x equal to 4.5. So that is one of our solutions. That's when the two equations are equal to one another. And then the second thing I look at, here's the other. You notice the graph is exactly the same. It's exactly the same, but my highlighted point that you see in yellow, the spider I call it from time to time, the spider is at 4.5. And now my spider is over here. So this is a different solution. So this is a solution, and it tells me right here, because we're interested in the x-intercept. The x-intercept solution is at negative 0.5, or negative 1/2. Okay, so as we take a look at this one, again, I'm going to graph. You're going to notice this a lot this year. I love to graph. The reason why? Because I like being right. You like being right too? Graph a lot. Take a look and see what it does. So we have x squared plus 6x plus 5, and this is greater than or equal to 0. So when I graph it, it looks like this. Now, you're going to hear a lot of different ways, a lot of different strategies to graph these. Some people will say greater than, you shade above or within or anything like that. I'm going to give you one method. There's more than one, but I'm going to give you one method, and I want you to do this because this will work all the time. What you need to recognize is there's two parts when we shade on an inequality like this. One of them is inside of the parabola, and the other is outside of the parabola. That's the only two places we would shade on a parabola. So my suggestion is to plot one of the points either in or out, and then if the statement is true, you shade where that point is. If the statement is false, you shade opposite of where that point is. So for me, the obvious choice is the origin. The origin is very easy to plug in because we're so good with our zero maths. We know how to add them and multiplying and all that stuff immediately. So when I plug in 0 for x, we should have an output value. It's either going to be true or it's going to be false. Now, if I plug in a 0 here and I square it, well, 0 squared is 0. So that's 0. Plus 6 times 0 is also 0. So you see why I chose the origin. Anything that has an x in it is just going to go away. So here's the question. Is the result a true or a false statement? Is 5 greater than or equal to 0? Of course it is, which means the area where the origin is the solution area. So this area inside here is not part of the solution, but everything outside is. So this is how I like to deal with parabolas. I like to test a point. Now, if the parabola does happen to go through the origin, I don't choose the origin. What I'll usually choose is a point like 0.5, 0.1, any of these different things, but we can check and see if our statements are true. So let's take a look at the next one. The next one I did not gather and graph. What I did on this one is I graphed both. I graphed the x plus 3, and I graphed the equation 7 minus 3x. Now, the reason why I chose to do it this way is just so we can see the variety on these things. I don't think that this is necessarily the best method. I would probably, like I told you earlier, rather gather and graph, but we can still take a look at this. So what we're going to do first off is label these things. So my equation with the positive slope is x plus 3, and that is the red line. And my equation with the negative slope, negative 3x, is the black line. So here's the question. When is the red line greater than, or you could use the phrase higher than, the black line? So as we move from infinity, we can see that the red line is lower all of these numbers until they finally are equal. They're finally equal at x equal to 1. So the black line is dropping at the same time the red line is rising. So once they get past this point, from then on, the red line will be greater than the black line. So they're equal at 1, but that's not what they ask me. They ask me when the red line will be greater than the black line. So they're equal at 1, and as we continue right, or greater than 1, our red line will be the solution. If you were to solve this by hand, you would end up with the same thing. Matter of fact, we can do this real quick. If we move this 3x to the other side, that gives me 4x. If I move the 3 over to join the 7, this would be 4x greater than 4. We divide by 4, x equals 1. If you're like, well, why didn't we solve by hand? You absolutely can solve by hand, but our focus today is solving by graphing. On our next slide, I'm going to show you how we use the intercepts, the functions on your calculator. All right, I'm going to let this video play for you. This is how we can use our graphing calculator to find the solutions. These equations you can just watch. You can try to put them in as quickly as you can. We're not going to use a spreadsheet on this. We're just going to use our graphing calculator. So here, let's take a look. What we're going to take a look at is how we can solve this equation, with a graphing calculator. So I'm going to start off by just having the equations already in here. We see the x squared minus 4 plus 1, and then the x minus 2. So we'll take a look at this graph. We see we do have two crossings. Remember, crossings indicate our solutions. So what I'm going to do to find this is I'm going to hit second, and then the calc button, which is trace. We'll go down to intersect. This is where the two lines intersect, and then we hit enter. It's going to ask me a few questions. You see it says first curve right here. The first curve on mine is the blue, so I'm going to hit enter. Sorry, hit enter over here. To my second curve, and then I can see it's on the red line, enter. And then the next one it's going to say is guess. And what I'm going to do is just slide up to about where they cross right here. Don't have to be precise, just be in the area. And then I hit enter. And then you can see my solution is at 0.6972244. Now I can see that there's a second at the 4 to 5 mark. That's actually the one we were asked about. So I'm going to follow that same sequence over again. So we'll get another chance to take a look at this. I'm going to go again second, the trace button, which is calc, the fifth button, which is intersect, and it's going to ask me for the first curve past the vertex. I want to make sure I'm past the vertex on a quadratic so it knows which side I'm talking about. I'm going to hit enter. Second curve, I'm going to hit enter again, and then I'm going to slide over to my intersection and hit enter. So there's my solution one more time.